Welcome again. In the last lecture, we have seen the construction of Cantor set and their properties. Now, let us discuss the construction of Sierpinski triangle, or sometimes it is known as the Sierpinski gasket. Just I recall how we constructed the Cantor sets. So, initially we took the unit interval, we divide the unit interval into 3 equal parts and remove the middle open interval, and we obtained the next step. Then in the first step we have 2 interval of length 1/3. In each interval we divide 3 equal parts and removed the middle open interval and obtained the next level set in the step 3. So, if we are continuing this process after nth iteration, we have 2 power n number of sets of length 1/3 power n. Then one can get the Cantor set as the intersection of all the sets. Finally, we will get the Cantor set. And what are the 2 important properties of the Cantor set? The Cantor set has the length 0 and it has the infinitely many points. Also, the each iteration we are removing the certain amount of interval from the closed interval 0, 1, and we obtained that the total length of removed interval is 1. So, these are all the some important properties of the Cantor set. In the same way, based on the Cantor construction process, we will do the Sierpinski triangle construction process. Let us begin with the equilateral triangle. Here we are starting from the equilateral triangle with 3 vertices. If each of this side length is equal, so we will take the each of its side length is 1. That means side length is an unit side length. Then now divide each side as a 2 equal parts, like this one. We are taking the mid part and just join this midpoint and remove the middle triangle. Then one can get this one, like this one. Here we removed this interval. So, here to here we divide the side as an 2 equal part and just join all the midpoints. Then here we removed this interior triangle. While removing this interior triangle, we are not removing the boundaries, only removing the interiors. So, here we have, there are 3 triangle 1, 2, 3, and the same process we are going to apply on these 3 triangles. It means the first triangle you can divide 3 equal parts and join these midpoints, then you will get this one and remove the interior of the middle triangle. And similarly, here you can divide as 2 equal parts and you can join these lines, then one can get this triangle. Here also you can remove the middle of the interior triangle. While removing the triangle, we should not remove the boundaries, only remove the interior points. And same thing you can apply on this third triangle. join the 3 midpoints and remove the mid one, then one can obtain this triangle. So, here in the first one to second one, by removing the interior of the middle triangle without boundary, we are getting 3 triangles. Here the first step to second step, we have 1, 2, 3 triangles. In each triangles we are dividing as 2 equal part its sides and joining the midpoints and removing the interior without boundary, then we are obtaining the second step. In same way, in the third process, you can join the midpoints, you will get this one, and join this midpoints, then you will get this one, and divide these 3 equal parts and joining this one, one can get this part. Now, here also we are removing the interior of the triangle without the boundaries. In same way, you can do it. Here we are removing the interior, here we are removed the interior, here we removed the interior, and here we are removing this interior and removing this interior and removing this interior. So, after the third step, we will get this type of triangles. Then, so after the 10th iteration, one can get this type of Sierpinski triangle. Now, if you are continuing this process as infinite number of time, then that final triangle we can call it as the Sierpinski triangle. So, what are the things we need to observe here? In the first iteration, we are removing one interval of the side length is 1 by 2, because here it is the unit side length. So, we are dividing as a 2 equal parts. So, this side length is 1 by 2 and this is 1 by 2, and we are joining this one and removing the interior triangle. Therefore, side length of this triangle is 1 by 2 and the side length of this triangle is 1 by 2. Similarly, the side length of this triangle is 1 by 2. So, what is the observation from the first step to second step? Here the triangle side length is 1, whereas here we have 3 triangle, each of its side length is 1 by 2. We have 3 triangle, equilateral triangle, and each of its size is 1 by 2. In the same way, this top equilateral triangle produced 3 more triangle, their side length is 1 by 2 power 2, because initially start from 1 by 1, then 1 by 2, then again we are dividing this one, therefore, this one is 1 by 4. So, it is 1 by 2 power 4, 3 triangle. Similarly, this left side of this triangle produce 3 triangles of side length 1 by 2 power 2, and similarly this triangle produced 3 triangle, their side length is 1 by 2 power 2. In the same way, in each iteration, each triangle produced 3 power, after the nth iteration 3 power n triangle, and each of its sides is 2 power n plus 1. So, if we are continuing infinite number of time, we will get the Sierpinski triangle. Now, let us try to find the area of the Sierpinski triangle. Okay, fine. The construction of the Sierpinski triangle start with the equilateral triangle S naught of the side length 1. Then the triangle S0 is subdivided into 4 smaller triangle using the line joining the midpoint of the side of length 1 by 2 and removing the middle triangle by leaving the boundaries. We are leaving the boundaries. The remaining set is S1. The relation between S1 and S0 is S1 is contained in the set S0. Now, in the S0 we have 3 sub triangle in the first iteration. Now, each of these 3 remaining triangle should be subdivided into smaller triangles with side length 1 by 4, and then in 3 middle triangles we are removing. By continuing this way, we can get the sequence of sets Sk, and the Sierpinski triangle is the limit of the sequence S0, S1, S2. This is the decreasing sequence, and the obtained is, the limit is obtained is S equal to intersection of all the triangles Sn, where n is a 0 to infinity. So, this intersection will give the Sierpinski triangle. Now, the set Sn after each iteration, Sn consisting of 3 power n triangle with the side length 1 by 2 power n. Then the total area of Sn is 3 power n triangle, each of its size is 1 by 2 power n, and the ratio of the area of equilateral triangle. So, what is the area of equilateral triangle, which is equal to root 3 by 4 a power 2, where a is the side length of the triangle. Now, what is the side length of our triangles in each iteration is 1 by 2 power n. So, take the power of 1 by 2 power n, and how many triangle in each interval we have, each iteration we have 3 power n triangles in each iteration, and its size is 1 by 2 power n, you can take the power 2, and 3 by 4 is the ratio of the area of triangle, equilateral triangle. Then this is in the nth step. Whenever this n tends to infinity, then one can obtain the area of the triangle. So, it is equal to 0. So, after the infinite number of iteration process, we are obtaining the equilateral triangle. That equilateral triangle we can call it as the Sierpinski triangle. The area of the Sierpinski triangle is 0. The area of a Sierpinski triangle is 0. Now, in the each iteration, we are removing the interior of the middle triangle, not on the boundary. Now, let us try to calculate the what is the length of the equilateral triangle. For that, the set S contains the boundary lines from the removed part of the triangles. Whatever the triangle we are removing the interior, not the boundaries. So, all the boundaries are present in the S. As Sn have 3 power n triangle of length 1 by 2 power n, the length of Sn is given by 3 triangle in the each iteration, 3 times 3 power n times 1 by 2 power n. So, then the total length of the Sierpinski triangle S is tends to infinity whenever this n tends to infinity. So, interestingly, the Sierpinski triangle exhibit the property of having 0 area while the total boundary length is infinite. What we discussed in the Cantor set, Cantor set are the infinitely many points, whereas the length of the Cantor set is 0. Now, here in the Sierpinski triangle, the Sierpinski triangle area is 0, whereas the total boundary length is infinity. Now, you can think about the area, length and the number of points will give the exact representation of these two objects. We have to think. Now, let us move on one more concept in the same way for the construction of Van Koch curve. In the construction of Van Koch curve, before starting the Van Koch curve, the Sierpinski triangle is constructed by the Professor Sierpinski. His lifespan is 1882 to 1969. Just you can note down the years. Next, we will construct the construction of Van Koch curve. In the Koch curve, we are taking the line segment and divide this line segment as 3 equal parts like a Cantor sets. Now, instead of the removing the mid interval, you just make it the side of the equilateral triangle like this one. In the Cantor set process, we removed the mid interval. Now, instead of removing the mid interval, we are just make it a side of an equilateral triangle. Then after the first iteration, we will get these 4 line segments, 1, 2, 3, 4 line segments. Now, this first line segment you can divide into 3 equal parts, make this mid one as the side of an equilateral triangle, then one can get this step. And in the second line segment, divide into 3 equal parts and make this mid one as a side of an equilateral triangle, then second one is represented here. Similarly, in the third one, divide into 3 equal parts and make it as a side of an equilateral triangle, one can get this part. So, first part is transferred to like this one, second part is transferred to like this one, and third part is transferred to this one. The fourth part is transferring as here we are removing this one and make it as a side of an equilateral triangle, and one can get this part. So, here we have only one line segment, here we have the 4 line segment, here each part has the 4 line segments. Now, you can consider only this part, do the same process, that means divide into 3 equal parts, make it as the side of an equilateral triangle, then one can get this process after these iterations. Fine. So, here length of the interval is 1, then what is the length of this interval? Line segment, this line segment interval is, we are 3 equal parts we are removing, therefore, each has the equal line segment as 1 by 3 side length. This is 1 by 3, this is also 1 by 3, this is also 1 by 3. Then this one becomes 1 by 3 power 2. Then this line segment into 1 by 3 power 3. So, after third iteration, one can get this type of structure. So, this figure is generated by after the 10th iteration. So, if you are continuing as an infinite number of times, one can get the Van Koch curve. So, how to construct mathematically define the Van Koch curve was, consider a line segment P naught of length 1, divide P naught into 3 equal line segment of length 1 by 3. Instead of removing the mid one, replace the midline segment with 2 segments both one side in the length 1 by 3. Now, P1 consisting of 4 line segment, each of length is 1 by 3. Proceeding the same steps for all line segment of P1, we can get P2 consisting 16 line segments, each of length is 1 by 9. So, what will happen if you continuing this process as n number of time? So, after the nth or kth iteration, the component Pk has 4 power k line segment, each of length is 1 by 3 power k. So, if you want to find the Van Koch curve, we need to continue this process as infinite number of time, then we will get the Van Koch curve. So, the Van Koch curve is obtaining by taking the iteration as infinite number of time, then one can get the Van Koch curve. Then let us try to find the length of the Van Koch curve. So, in the construction of Van Koch curve, the component Pk consists of 4 power k line segment, each of its length is 1 by 3 power k. So, if you are taking the limit of these two quantity, then one can get the length of the Van Koch curve. So, length of the Van Koch curve is 4 by 3. The 4 by 3 is greater than 1. Whenever you are raising the power k 1, 2, 3, then it approaches to infinity. Therefore, the length of the Van Koch curve is infinity. And Van Koch curve has some other different mathematical properties. That means, it is a nowhere differentiable, but continuous function. Van curve is continuous everywhere, but nowhere differentiable function. So, what is mean by the differentiability and continuity? So, now let me briefly explain why this function is continuous everywhere and nowhere differentiable. At each stage, the number of corners, that means the sharp nodes, is increasing. We cannot find a single tangent at any point in the Koch curve. Therefore, it is nowhere differentiable, however the curve is continuous. You can observe here in the each corner, we are starting with the smooth one, the corner you can, this corner, it is a sharp edge, therefore, the function is not differentiable at this point, and the function is not differentiable at this point, and the function is not differentiable at this point. Suppose the function is differentiable at any point, means it is should be a smooth curve like this one. Whenever there is a sharp edge, if you are drawing the tangent line, it will touches the curve more than one point, therefore, the function is not differentiable. So, it has here 3 sharp edges, therefore, it is not differentiable these 3 points. Similarly, here it is in this stage, this is not differentiable at these points, all these sharp points, and here also it is not differentiable at all these points. So, if you keep on increasing this iteration, the sharp edge is increasing, therefore, if you draw the tangent line, it will touches the curve at 2 times, therefore, the function is not differentiable at any point, therefore, the Van Koch curve is nowhere differentiable functions, whereas this curve is a continuous curve. So, the Van Koch curve is an example of continuous everywhere, but nowhere differentiable curve. This Van Koch curve is constructed by Professor Van Koch, here life spanning from 1817 to 1924. One thing you can observe from all these 3 construction process, that means the construction of Cantor set and the construction of Sierpinski triangle and the construction of Van Koch curve, all the sets are regressively constructed. All are having some complex property. Why I am calling it is a complex property? Cantor set is the example of uncountable set which has the measure 0. That means it has the infinite number of points, whereas its length is 0. And the Sierpinski triangle, it has the area 0, whereas their boundary length is infinite length, the area is 0. And in the Van Koch curve, it has the infinite length. So, one can think about all the three sets. They are defined regressively, whereas length, area and the number of points are either 0 or infinity. So, do you think that these quantities length, area and number of points will give the exact representation or give any information about the sets? So, these three sets are quite complex natures, or we can call it as it has the irregular natures. So, in order to study this type of irregular natures, Professor Benoit B. Mandelbrot introduced the term called the fractals. So, what do you mean by the fractals? Fractal is derived from the Latin word fractus, meaning fragmented or broken. In the Professor Benoit Mandelbrot introduced the concept of non-integer dimension and self-similarity extensively seen in the nature object, sparking of Mandelbrot to coin the word fractal, derived from Latin adjective fractus, meaning broken or fragmented. There are two terms are here important. One is non-integer dimension and self-similarity. Now, whatever the object we studied or discussed so far, Cantor set, Sierpinski triangle and Van Koch curve, it has some irregular nature. So, in order to study this type of irregular nature, Professor Benoit Mandelbrot introduced this concept. So, his life spanning from 1924 to 2010. So, these three sets are invented before even the birth of the Professor Benoit B. Mandelbrot, but he introduced some concept called the fractals, which helps to understand the nature of all these irregular sets. So, he give the definition of fractal in two ways. One is based on the dimension, another one based on the self-similar property. Let us discuss what is the fractal in terms of two type of definition. So, Mandelbrot defined the fractal to be a set with the Hausdorff dimension strictly exceeds its topological dimension. That means, you can take a set, find the Hausdorff dimension and the topological dimension. If the Hausdorff dimension of the set is strictly greater than the topological dimension of the set, then we can call it as the set is a fractal. So, this definition is based on the dimension theory, whereas he gave the alternative definition which based on the self-similar property. A fractal is a shape made of parts similar to the whole in some way. So, what it means? A A fractal is a shape made of parts similar to the whole in some way. This property is called the self-similar property. You can take an object and take its parts. If the part is the resemblance of the whole thing, then we can call this set as the self-similar nature. One can ask the questions whether this part is exactly reflecting the whole or approximately reflecting the whole. Based on this, the self-similar property is classified into two types. One is random self-similarity, another one is exact self-similarity. If an object possesses an random self-similarity, then it is called the random fractal. If an object possesses an exact self-similarity, it is called the deterministic fractal. Now, whatever the set we discussed now, Cantor set, Sierpinski triangle and Van Koch curve all are possess the self-similar property. Let me explain how these sets are possess the self-similar property. Here you can see in the construction process of the Cantor set, we are started from the closed interval 0, 1 and arrived the set after the infinite number of iteration. You can take this part or this part. If you are taking the left part, this is exactly match with the whole thing. Similarly, if you are taking this right part, this is also exactly match with the whole thing. Now, one can observe from the Sierpinski triangle construction, if you are taking any smaller part of this triangle, it exactly resembles all the triangles. That means the whole triangle, any part, we can take the randomly any part, it exactly resembles the whole thing. Therefore, it also possesses the self-similar property. Then similarly, if we are going to the construction of Van Koch curve, one can observe that if you are taking any smaller part, it is also similar to the whole. Maybe I will take randomly here. This also exactly resembles the whole things. Therefore, this also possesses the self-similar structure. So, this is called the self-similar property of Van Koch curve and Sierpinski triangle and the Cantor set. So, all these sets are possess the self-similar property. That means, a part of the object is a resemblance the whole. Therefore, we can call this as a fractal object. Now, the question is whether based on the self-similar property, we can conclude the fractal, the objects are fractal. Whatever the next definition. Now, Cantor set, Sierpinski triangle and Van Koch curve all are possessing the self-similar property. Therefore, we can call it as a fractals. Then what about the next definitions? So, what is the next definition of the fractal? Mandelbrot initially defining the fractal as a set with the Hausdorff dimension strictly exceeds the topological dimension. So, based on this also we can say the object is fractal or not. Now, these are all some sets which are naturally appearing. Let me explain the fractal nature of this object, then we will come to the dimension theory. If you are taking any part of this object in the fan, in this figure, you can consider the figure A. If you are considering this figure, the first part, if you are taking this part, it exactly or not exactly, in somehow it is similar to the whole. In the lightening, if you are taking any part, it may resembles the whole, and also if you are taking the branches of the tree, it is also resembles the whole, and the broccoli also if you are taking the part, it resembles the whole. Then what is the difference between this resemblance and the previous classical examples, Cantor set, Van Koch curve and Sierpinski triangle resemblance? There they exhibit the exact self similarity, whereas these sets, fan leaf and lightening, branches of the tree, broccoli, exhibit the random self similarity. That means the part of this object not exactly resembles the whole, whereas in the statistical manner or approximately it is resembles the whole. Therefore, these are all called the random fractals. So, previously discussed 3 sets are the example for the exact fractal, and these 4 objects are the example for the random fractal. Now, how to conclude that an object is an fractal based on the self similar property? You can think, you can take the line segment, you can divide as 2 parts. Then obviously, if you are checking the left part and the whole, their structure is same, the size is smaller, it resembles the whole. Can we conclude this as a fractals? Then what is the difference between the line and the fractal object? Since the self similarity is not new for us, you can take any Euclidean object, it obviously possesses the self similar property. Fractal means it has the self similar property, whereas one cannot conclude that based on the self similar property the object is a fractal object. So, for confirming this one, we need to go for the dimension theory. So, how to define the fractal in terms of dimension? For that, Professor Kenneth Falconer gave the following property which guarantee that a set to be a fractal. First one, a fractal exhibits a fine structure at arbitrary small scale, nearly the same at every corner, on a large scale and on a small scale. Further, no smooth parts should be observed by scaling. It has a Hausdorff dimension that is in general strictly greater than its topological dimension, same as the Mandelbrot definition. It is recursively defined through initiators. Fractal is finite, sometimes infinite copy of itself. In general, fractal is too irregular to be described in traditional geometry. So, one can conclude if the set possesses all these properties, then we can conclude it has the fractal object. If the set possesses all this property, we can conclude the object is a fractal.